Okay, college algebra 3.3, B as in boy, and we're starting on absolute value functions, still in chapter 3, lesson 3, and I'm not going to go into all of the theory, the definitions of the absolute value function. If you want to know exactly where they came up with the function and how it all works, feel free to read about the absolute value functions, but I'm, for the most part, just going to show you what the absolute value function looks like as a graph. Okay, it looks like that because on the x-axis, no matter what number this is, it's going to map to a y value that's positive. No matter what number an x is in the negative way is going to graph to a positive y value. It's never going to be down here because the absolute value of any number is, let me just do a little line graph, and just as a reminder here, all absolute value is how far is that number from 0. So if we have a number that is here, it is 1, 2, 3, 4, 5 away from 0. If the number is here at -5, it is still 5 units from 0. It's just going in the negative direction. So basically what that's saying is whenever you're measuring distance, whether you're going north, east, south, or west, you are always going in a positive direction. It's not like you go to McDonald's 5 miles away and then you come back 5 miles and now you're going -5 miles, and when you get home you really haven't gone anywhere. No. It's just the distance from 0. That's why it's always a positive number, because distances are always positive. So that's why we get a graph that looks like that. All right, so solving these absolute value equations are not really tricky, but you've got to be thinking through what you've got here, because, let me give you an example here. The absolute value of x equals 5. We know that x has to equal 5 or -5, okay? Because if this is 5, it's going to be 5. If it's -5, the absolute value, the distance from 0, even though it's -5, is going to be 5. So, actually, what we have are two different options for an answer. Now, when we do the equations, we're going to end up with the same thing. So if you look at example number 6, we've got x minus 3 equals 9. Now if we follow that rule, that the absolute value of x is 5, then x equals 5 or -5, which means the positive or negative of our right-hand side there. The same is going to be true here, okay? So, x minus 3 is going to be equal to 9, or x minus 3 is going to equal -9, just like we said 5 or -5 here. So what that means we end up doing is we end up solving this equation twice. And I'm just going to write this over here. So, x equals 12, or x equals -6. Okay, so we have two answers there for our x value. X is 12, or x is -6. Now, if you look at B in example 6, we have 2x minus 4. The absolute value equals 8. Which means, again, we're going to take the absolute value sign off and set it equal to +8, and then set it equal to -8. Solve for x, and we get 6 and -2 for our answer. All right, let's look at C, because C is going to be a little bit different. I'm not really different as far as, oh great, it's kind of like English. Every time you turn around there's a new rule. No, it's just going to be a little bit longer, and as long as you follow the same system, it's fine. It's just in this one we're going to end up with 4 answers because of this. Okay, so we get x squared minus 5x equals 6. and x squared minus 5x equals negative 6. So, if you remember what I said a while ago, the exponent that is the biggest, in this case x squared, tells you I'm going to have two answers to this problem. I'm going to have two answers to this problem. So totally for this whole equation, I'm going to have four answers, four places where my x is going to be on the graph. All right, so I solved this one, and I'm going to use, I can just look at this and say, yeah, I think I can do factoring, because I can change this to x squared minus 5x minus 6 equals 0. And I have an x here and an x here, a 6 and a 1. I need to get a negative 6 and add to get a negative 5, so that means I'm going to look like that. So x equals positive 6 or negative 1. Over here I do the same thing. X squared minus 5x plus 6 equals 0. And again, I break it down into two binomials, and I get an x and an x, and a 3 and a 2, and they're both negative here because I needed to get a positive there, which means my x equals 3 and 2. So see, I have four answers there. And also, it does give you an idea if you want to graph this. Middle of page 203, right above figure 3.29, tells you how to use your graphing calculator and be able to graph that. All right, brings us to power functions. Now, power functions are really not too bad. It's just using squares, cubes, fourth roots, that kind of thing. And if you look on page 204, it gives you some different graphs. And what I'm going to do is I'm going to give you a page from a different college algebra book that I use. Let me do that for you. Okay, so this is from the back cover of an old college algebra book I have. And what I like about this is it just gives you an idea of what shape a graph is going to be when it's in a certain format. So let me make this just a little bit bigger. So we have squaring functions. We have quadratic. You know, there's the square root function. You know, it goes that way and that way. A cubing function. Something that, I'm sorry, I'm doing this wrong. Okay, squaring function would be this one, where you have x squared, a quadratic function there. There's another quadratic function, same kind of thing. Another option, only it's opening down. So these are just some examples of quadratic functions. This is an example of an absolute value function, and you've got linear functions that are lines. If, for instance, you have an x cubed, your graph is going to look something like that. So it kind of gives you an idea when you're graphing these functions from the equation whether or not you're on the right track. Does my cubing function, if I have an x cubed, does it look like that? Well, yeah. Well, then it's probably pretty close to right. And there's a cubed root. So if you have a radical with a 3 as your index, that's kind of what it's going to look like. So it's all these different options about what a function is going to look like. It's kind of nice. I would save that or put it in your notes or something for later, because it's just kind of nice to be able to refer back to it and say, okay, I got this weird shaped figure. I wonder if it's supposed to look like that. But anyway, that's kind of what they're talking about on pages 204 to 205, just the different functions and what they look like here. And it doesn't really explain a whole lot about what in the world we're doing with power functions, but let's just go with example 7, wingspan of birds, and kind of get an idea of how to use these power functions here. So we have L equals 2.43 W with an exponent of 0.3326. Let me make that 3 right here a little bit better. Okay, so that is the power function for this particular example, where L is the wingspan in feet, and W is how much the bird weighs. So what I want to do, rather than go into a lot of stuff on this particular problem, go ahead and read through what they're doing there. I mean, I'm just going to basically do exactly what they say to do there, so you can just do that on your own rather than listen to me ramble about it. But one of the things I want to go over real quick is how to input that in your calculator. Okay, so if you have 4 to the 3.67 power, or something, similar to that, you have a key on your calculator that looks like this. So what that means, if you want to find 4 to the 3.67 power, you push 4, then you hit this key, and then you hit 3.67, and that will give you 4 to the 3.67 power, which is 162.017 if you want to try it out on a calculator. So that's all I really wanted to show you there. Let's jump to root functions. And again, referring back to that table I gave you of what the different graphs look like, notice that on the side panel of page 206, well, even up at the top, they give you different shaped graphs there. The first one is a square root function. The next one is a cubed root function. So just be sure to look at those. And the last one is a reciprocal function. But let's look at root functions right now. And this is one method. And again, the book doesn't explain this terribly well. But let me kind of go into it a little bit. If I have the cubed root of 3, or the square root of 3, I can change that and get rid of this sign here, because sometimes that sign just causes all kinds of grief. And I can rewrite it as 1/2, 3 to the 1/2 power. And if I want to change it back, I can go from here to here. And let me just go over, review a little bit about the radical sign. There is an assumed 2 there, okay? Which means what number times itself twice will give you 9, and that will be, plus or minus 3. The primary root would be the positive 3, and so we'll kind of stick with that, at least at this point. But this number, that number 2, is called an index, okay? And the 9 is the root. So the index is 2. Notice where the index is when you change it to what's called exponential form. When you have an exponent, you just put a 2 in the bottom. You put it under a 1. The cubed root of 8 is going to be 8 to the 1/3. Okay, so the 1 is up here, the cube is down here. Now what if I had something like x squared and I'm taking the cubed root of it? I'm going to write it as an x. I'm going to put the index on the bottom, and the exponent, on all the other ones it was 1, but in this one the exponent is a 2, so the 2 goes up there. So this is the exponential way of writing that. And I would definitely put that in your notes just so you remember what that looks like. Because you can write any radical as an exponent, which makes it really, really easier to do when you're, well, let me give you an example. If I wanted to take the cubed root of x squared and multiply it by the 4th root of, x squared of x to the cubed, how would I multiply that? But if I changed it to exponential form, I can do that. Because when you are multiplying things with exponents, like x squared times x cubed, you add the exponents, x to the 5th. If I have something like this, I find common denominators and I add the exponents, and therefore I can actually multiply those. Whereas when it's in this form, I'm like, oh my gosh, I can't do anything with that. Okay, so it's good to be able to switch those back and forth. And then once you get an answer here for this, you can switch it back to radical form if you want to. So anyway, that's kind of a good thing to learn in the book. Kind of goes into it a little bit in the little green box. The root function is a function of the form y equals ax to the 1 over n power, or y equals a to the nth root of x. It doesn't really explain what's going on. It just says this is what it looks like. So hopefully that gives you a little bit of an idea. Okay, the reciprocal function. If I have y equals x to the negative 1 power, that is the same, this is the same as 1 over x. Okay, so if I have a negative exponent, and that you can call it whatever you want, the reciprocal function, a negative exponent, whatever, there's a certain method to solving this. If I have x to the negative 2 over y to the 5th, what does that mean? Okay, it means that this negative is telling you that the number or letter before it and the number or letter after it, okay, this one right here and this one right here, it tells you that this is in the wrong position. It's in the numerator position, which is okay, but it shouldn't be there. It's actually in the denominator position. So when you put it in the denominator position, back where it's supposed to, the negative goes away and it disappears from the numerator. Now there's nothing up there, but there's always an assumed 1. You never have nothing in the numerator or denominator. It's always a 1. Okay, notice this here has a positive 5 on it, so it doesn't change. It's not, that doesn't have a negative there telling you it's in a position that it doesn't belong. But if I had, let's see, x to the negative 3, y squared over z to the negative 4, k to the 4th power. What does that mean? It means that that's in the wrong place, so I'm going to put it down here. It says that's in the right place, so it's going to stay there. That's in the right place, so it's going to stay there. This has a negative, and it's in the wrong place, so it's going to go up here. That way, all my exponents now are positive. If I wanted to move all the exponents to the bottom, I can do that. I just have to change. I just have to tell the reader that they're in the wrong place, that the z and y are in the bottom, but they shouldn't be there, so I'm going to put a negative on there. The k and the x are in the right place, so I'm going to leave those alone. Okay, so you can move your exponents around from up or down, but you have to change the sign of the exponent to its opposite if you're going to move it to a different place. So that's pretty much what the reciprocal function tells you. All right, I'm going to stop this video right here because I'm already 18 minutes in, and we'll start on 3.3c.